All right, so today what we're going to be doing is real Earth motions. So we're going to be looking at what kind of motions the Earth makes. All right, so like we mentioned with the motions of the moon page and notes, motions of the Earth also are responsible for giving us units of time. And the first motion of the Earth that we're going to look at is rotation. So rotation is when the Earth spins on its axis like that. That is rotation. All right. Now, the unit of time that is derived from Earth rotation is the day. So one Earth rotation is a day. And currently days are 24 hours. But that wasn't always the case. If you go back like a few billion years, the Earth actually used to spin faster than it does today. So a day might have been like 15 hours or 12 hours, something like that. What happens is though, the gravity from the moon acts like a brake and is gradually slowing the Earth's spin down. So, 100 million years from now, an Earth day is likely going to be a little bit more than 24 hours. But now, an Earth takes 24 hours to one Earth rotation. The speed at which the Earth rotates. The Earth rotates at 15 degrees per hour. And we talked about that a little bit before when we were doing latitude and longitude, because we said that there's 360 degrees in a circle divided by 24 hours. So the Earth rotates 15 degrees of longitude per hour. So that's how fast it spins, and you've seen that number come up a few other times that we've talked about, because things in the sky, like the sun, moves across the sky at 15 degrees per hour. But what's really happening is the sun's not moving. It just looks like it's moving because the Earth is rotating 15 degrees per hour. Or the stars during the course of the night. The stars appear to move around Polaris at 15 degrees per hour. Again, the stars are staying in the same spot. It just looks like it's moving, they're moving 15 degrees per hour because the Earth is actually rotating. Now, if you ever looked at a globe, you'll notice that wherever you buy globes, the Earth is never straight up and down in a globe. The Earth is always tilted. And the reason for that is because the Earth's axis of rotation is tilted at 23.5 degrees. So what scientists think must probably happen is in Earth's early history, it was straight up and down, spinning along, minding its own business. Then what probably happened is, bam-o, probably got hit by a big asteroid or something. That kind of knocked the Earth off a little bit. So the Earth's axis is tilted 23.5 degrees. All the other planets' axes are tilted to various amounts of degrees. Some of them are only tilted like 5 degrees or so. Other ones like Uranus is actually tilted at 90 degrees. So Uranus actually spins like this in its orbit. Now that tilt is significant because it's because of that tilt that we have the seasons. Because what happens is the Earth's always tilted the same direction. So when we're on one side of the sun, the northern hemisphere is tilted towards the sun, so most of the energy is hitting the northern hemisphere, and then not very much is hitting the southern hemisphere. So this, for us, the northern hemisphere would be summertime, because most of the energy is hitting us here, up here. 6 months later, in December, it's basically tilted like this. So now most of the sun's energy is hitting the southern hemisphere, but for us up in the northern hemisphere, it's coming in at a much lower angle. That's why it's cold in the wintertime. So it's that tilt is what causes the seasons. If the tilt was less, if the tilt was maybe 10 degrees, we'd still have the seasons, but there wouldn't be as big of a difference between summer and winter. If the tilt was more, like at 30 degrees, then you'd find more extreme temperatures between summer and winter. All right. Now, evidence that the Earth rotates. So how do we know the Earth is spinning, right? Because it doesn't feel like it's spinning. Well, it's actually a little bit more difficult than you might imagine, because a lot of the things that are caused by the Earth spinning aren't necessarily proof that it spins. So for example, the rising and setting of the sun is caused by the Earth rotating. However, if the Earth was standing still and the sun was going around the Earth like that, the sun would still rise and set. So that's not proof that the Earth rotates. Or the fact that the stars move in the sky, all right? That's caused by the Earth rotating, but it's not necessarily proof the Earth rotates because there's other ways of explaining it. You know, if the Earth was standing still and the stars were actually moving, that would mean that the Earth was standing still and the stars were rotating. So actually proving the Earth rotates is a little bit more difficult. Now nowadays it's easy because you can send up a satellite or spacecraft that can look at pictures, can videotape the Earth, and during the course of the day they can actually see it spin. But observations from the ground are a little bit trickier. All right. The two main pieces of evidence we use to show us that the Earth rotates are the Foucault pendulum and the Coriolis effect. All right, so we're going to look at the Foucault pendulum first off. Named after a Frenchman whose last name is Foucault. What a pendulum is a thing that swings back and forth like that. Like a grandfather clock has the big thing that swings back and forth. It's like a pendulum. All right. Now the significance of a pendulum is with a pendulum, when it's swinging back and forth, the momentum keeps it going back and forth in the same direction, even if the thing that's holding it is moving. And it's based on that we show the Earth is rotating. So I'm going to do a little demonstration for you up here. All right. So right here, there I have a pendulum swinging back and forth. All right. Now, with Foucault's pendulum, it works best if you do it at the North or South Pole. It works other places too, but it works best if I do it at the poles. So let's say I'm doing it at the North Pole. All right, so I go to the North Pole, and again, with the pendulum, the thing you should notice about it is that the momentum keeps it swinging back and forth in the same direction. All right. So let's say I have this pendulum, and what I do with it is I set up like a circle of like cans around the pendulum like this. I set up a bunch of cans around the pendulum like that, and what I do is I get the pendulum swing, right? I get the pendulum swing, and the initial swing back and forth, it's going to knock over this can, and it's going to knock over this can, all right? Bam, bam, all right? What's going to happen during the course of the, what's going to happen during the course of the day is it's going to knock over that one, then that one, then that one, then that one. The pendulum is supposed to stay swinging back and forth in the same direction, but the cans rotate underneath it, and what will happen is during the course of the day, all those cans get knocked over. So we know the momentum of that pendulum is in the same direction, and that is the Earth that is moving underneath it. So that is proof. All right, so the pendulum's going back and forth, and then the Earth moves underneath it. So that is proof that the Earth is actually rotating. Now, a lot of museums have like big giant versions of these. I know the Smithsonian has one. Some colleges have them too, like the Science Building at SUNY Geneseo has one. The Science Museum in Chicago has one. They have these big giant ones, so during the course of the day, you can see how the Earth is rotating underneath it. But anyway, so that's the Foucault pendulum. Okay, next piece of evidence is something called the Coriolis Effect, and that's where the wind gets bent or the paths of water gets bent. All right. So like, if you ever know, like here in New York State, the winds almost always come out of the west. All right, it calls the prevailing winds. Well, the reason for that is the Coriolis Effect, and what the Coriolis Effect is when the rotating Earth causes winds to bend certain directions. So again, I'm going to use that same setup I just used to show you the Foucault pendulum to show you the Coriolis Effect. All right, so I don't need this part of it anymore. All right, so right here is a straight edge. All right, so again, I'm looking down at the polar version of the Earth. So there's the North Pole right there, and then as I go outward, I'm going towards the equator in any direction. Okay. Now, let's say that there was a wind that was going from the North Pole to the equator. Okay. Now, I'm going to make a nice straight line. So there's a straight edge right there. Now, if there was a nice straight wind and the Earth was not rotating, what I'd have is a nice, again, there's a straight edge right here, a nice straight line like that. So right there's my nice straight wind. All right. However, the Earth does rotate. All right. So now what's going to happen is I'm going to take my marker and I'm going to make my marker go along that straight edge again. But what I'm going to do now is I'm going to have the Earth rotate underneath it. And what you'll see is my marker's going in a straight line. However, the path on the Earth's surface now looks bent. All right? The path on the Earth's surface right there now looks bent. Now my pen was going in a straight line, but it was the Earth that was moving underneath it to make it bent like that. That happens with air moving across the surface. It can also happen with water. That bending that is a result of the Earth rotating underneath it is what the Coriolis Effect is. All right. So the Earth fluids moving across the surface like water or wind, they get bent by the Earth moving underneath it. And because the Earth is always rotating the same direction, that causes the winds to almost always blow from the same directions. So like in New York, the winds almost always come from the west. If you go a little bit south of Florida, that latitude, the winds almost always blow from the east. And again, that's the result of the rotating Earth. The Earth's always rotating the same direction, so it's always bending the winds at the same way at various latitudes. All right. So that is evidence of rotation. That is evidence of rotation. Okay, next. Motion, revolution. All right, revolution, motion around the sun in a path called an orbit. So here's the sun, Earth going around it like that is revolution. And a couple things. The unit of time that's based on one Earth revolution is the year. All The speed at which the Earth revolves, well, there's 360 degrees in a circle, and it takes 365 days about to go around once. So 360 divided by 365 is about 1 degree per day. So, this would be like January 1st, January 2nd would be 1 degree farther over, January 3rd would be 1 degree farther over, January 4th, 1 degree farther over. So every day the Earth is revolving 1 degree over in its path approximately. Now the length of a year is not exactly 365 days. It's about 365 and a quarter days. That's why we have a leap year every 4th year to compensate for that extra quarter day. And it's actually not even exactly a quarter day. It's a little bit off of a quarter day. So every 100 years they have to make another adjustment. Every 400 years they have to make another adjustment to the calendar and so forth. But it's about 365 and a quarter days. So every 4 years is a leap year. All right. Evidence that the Earth revolves. All right. So how do we know the Earth is revolving? We see different star constellations throughout the year. All right. All right, so let's say here's the sun. And here's the Earth. All right. And here's some stars over here. And then there's some stars over here. All right. Now, when the Earth's in this position here, if I'm facing that way on the Earth, it's daytime. If I'm facing that way, it's nighttime. So I can see these stars at night, but I won't be able to see these stars because basically the sun's going to be blocking them out. All right. So when the Earth's there, I can see these stars, but I can't see these stars. 6 months later rolls around. Now I'm over here, and at nighttime I can see these stars, but when I look that way, I can't see these stars anymore because the sun's basically blocking them out. So as the Earth is moving around in its orbit, I see different star constellations throughout the year. Now, you may be thinking to yourself, I can see the Big Dipper all year round. What's up with that? Well, what you have to remember is this is only a two-dimensional drawing, right? This is what's going on along this plane here. There's also stars that are out here. That's where Polaris and the Big Dipper and stuff. The ones that are out here are the ones you can see all year round, or the ones that would be like in the other room there on the other side of the board would be the ones you can see all year round. It's the ones on this plane are the ones you only see certain times of the year. And the star constellations on this plane are probably the ones you've heard about because they have names like Leo and Cancer and Capricorn and Sagittarius and Virgo and Pisces and stuff like that. Those were the signs of the zodiac come in. Those are the star constellations that are along this plane that you only see certain times of the year when the Earth is in a certain spot as it's revolving around the Earth. All right. So that's the evidence that the Earth is revolving. We see different star constellations throughout the year. Okay, the third motion Earth makes, precession. That's the Earth's wobble. All right. Now, when things spin, when things rotate like that, they don't normally rotate perfectly. What happens to them as they rotate, they also kind of wobble like that when things spin. All right. That's what precession is. And I could demonstrate precession with a gyroscope. All right. So here Here is a gyroscope. If you've never seen one before, it's kind of an old-timey toy, a scientific toy at that. And there's all sorts of crazy things you can do with the gyroscope. You can get them to balance on the tip of your finger. You can get them to walk on a tightrope, basically. But besides being a toy, they actually have an important purpose, like in spacecraft, to help orientate spacecraft and stuff like that. But for right now, we're just going to use it to demonstrate precession. All right, so here's my gyroscope. I'm going to pull the string and it's going to start to spin. But as it's spinning, it's going to stand up. But if you notice, as this thing is spinning, it's also going to kind of move around like that, especially when it starts to slow down. That's what precession is. All right, so I give her a spin. See the top there? It's kind of wobbling. The top there is kind of wobbling. That's what precession is. All right. Now, you don't hear about precession as much as you do about rotation and revolution. And the reason being is rotation, it takes a day for one rotation. It takes a year for one revolution. The amount of time it takes to complete one wobble, the amount of time it takes to complete one precession, is about 26,000 years. So it takes a really long time to complete one wobble. So it doesn't really affect us too much during our lifespans. Some things that will affect, well, one, for example, is where the North Pole, where the North Star is. Because right now, the reason why Polaris is the North Star is there's the North Pole. Polaris is directly above the North Pole like that. But the Earth wobbles like this. So Polaris is only temporarily the North Star. In a few thousand years, when the Earth's maybe tilted like that, some star over there is going to be the North Star. So Polaris is the North Star now, but as the Earth wobbles like this and where the North Pole is pointing, it's eventually going to point to other parts in space. So there'll be other stars that possibly won't be as easy to find as the North Star. So that's something that's going to change within a few thousand years. Now, it's a combination of these things, a rotation and revolution, is what gives us the seasons. All right, the fact that the Earth revolves around the sun and the fact that the Earth's axis of rotation is 23.5 degrees, because what we have happen is in June, the Earth is tilted like this, where the North Pole is tilted towards the sun's rays, so the sun's rays are hitting mostly in the northern hemisphere. So for us in the northern hemisphere, this is going to be our summertime, because if we're tilted towards the sun and the northern hemisphere is getting more energy, it's going to be warmer. If you're in the southern hemisphere, you're tilted away from the sun and it's going to be cooler. Also notice where the sun's rays are shining directly on top of. They're shining directly on top of 23.5 degrees north. Because remember we said that the sun only ever shines directly overhead near the equator between 23 north and 23 south. Well, here's where it's shining directly on top of 23.5 degrees north. Right? 6 months later, when the Earth's over here, it's still tilted the same direction, but now that we're on the other side of the sun, now the sun's rays are hitting mostly in the southern hemisphere. All right. So for us, in the northern hemisphere in New York, it'd be wintertime because the sun's rays are hitting at a lower angle up there. In the southern hemisphere, they'd be experiencing their summertime. All right. So when the North Pole is tilted towards the sun, it's June 21st, summer for us. When the North Pole is tilted away from the sun, it's December 21st, and for us, it's wintertime. Now, in March and spring, this is kind of hard to draw in a two-dimensional diagram here. The Earth's axis is still tilted. However, the Earth's axis is not tilted towards the sun, and it's not tilted away from the sun. In September and March, it's tilted perpendicular to the sun. So it's not tilted towards or away, it's tilted this way. So on those days where the sun's rays are hitting straight down on top of is at the equator. So that's what the diagram is trying to show you. March 21st, the sun's shining directly on top of the equator right there. That's springtime. And then September 23rd, the sun's rays are shining directly on top of the equator right there. So that's fall. All right, so that is how the Earth's rotation and revolution causes the seasons.